Hello dear students, today we will be discussing about measurement of inductance and capacitance. So Maxwell's inductance bridge is used to measure the self-inductance of the circuit. So we are able to measure the unknown self-inductance of a coil using this Maxwell's inductance bridge. Again, it is an extension of the bridge that we have already learned, which is a Schering bridge. It works on the principle of comparison as well as balance. So just like the Schering bridge, the unknown inductance is determined by comparing with the known value, and under the balance of the bridge we are able to find out the unknown value of the inductance. So this is the structure of a Maxwell's inductance bridge. So in this bridge, arms BC as well as CD are purely resistive. So these R3 and R4 are non-inductive resistances, and the balance depends on the values of arms AB and AD. So in arm AB we are connecting an inductor which is unknown in nature. The value of inductance is unknown and it is having a resistance of R1. So since inductor is a coil, it will be wound using a conductor, you will be having a resistance of that. So we are representing that as a series resistance along with the value of inductance I1. So this is the unknown quantity, and L2 is a known value, a known inductor which is variable in nature, and R2 is the resistance of this particular inductor L2. Now the bridge can be balanced by varying L2 as well as it could be varied by also balanced by using R3 and R4. So R3 and R4 can be made variable, and that also can be varied. The idea is to make the bridge balanced by bringing this current I D equal to 0, so that whatever the current that is flowing through this AB, that will be same as the current that is flowing through BC. Okay, so you'll have a current flowing like this, and you will have another current you will have a current flowing like this, and you will have another current flowing like this. So this is your balance condition. Okay, so we'll see how it works. Yeah, so this is the current that is flowing. Now at balance we can see that your E1, this E1 will be equal to E2 because you are having B and D at same potential. So once B and D are at same potential, what you can say is that your voltage E1 will be equal to E2. Similarly, your voltage E3 will be equal to E4. So we are making use of these two simple conditions to find out the unknown values. Now what you can do is that I1 into R1 plus j omega L1, which is the impedance of this branch, equal to I2 into R2 plus j omega L2, okay? Or I2 into I1, you can call it as Z1, equal to I2 Z2. And from this condition E3 equal to E4, we get I1 R3 is equal to I2 R4. I1 into R3 equal to I2 into R4. Now dividing this equation A with equation B, what we will get is that R1 plus j omega L1 by R3 equal to R2 plus j omega L2 by R4. Okay, so this is the balance equation that you get. Now you can equate the real and imaginary parts. Once you equate the imaginary parts, what you will get? So imaginary part in the sense, this will be imaginary part. of this particular equation, and this will be the imaginary part of this equation. So it will be L1 by R3 equal to L2 by R4. So the unknown value L1 inductance can be obtained by R3 by R4 into L2, where L2 is a known inductance and the resistance is also known. And if you need to find out the value of R1, if you are trying to find out the value of R1, you can equate the real parts. So if you equate the real parts, real part of the equation, we will have R1 by R3 equal to R2 by R4. So here R1 will be equal to R2, R3 by R4. Now the value of R1 can be obtained by balancing the R3 or R4. Okay. So you will be adjusting L2 as well as any one of these resistance to make the detector current or the galvanometer current to be 0. So once you do that, automatically you will get the value of L1 as well as R1. So once you get L1 and R1, the whole unknown value of inductor is solved. R1 plus J omega L1. So in that way we are able to find out the inductor value, and if you are particularly recurring or going for the inductance value only, you can equate the imaginary parts and get the inductance value, unknown inductance value. So that's how the Maxwell's inductance bridge works. Now we will move on to the measurement of capacitance using a bridge known as Schering's bridge or Schering bridge. Now this particular Schering bridge can be used to measure the capacitance value of unknown capacitor. In addition to this, this also can be used to understand the properties of insulators like dissipation factor and other study of capacitor bushing, insulating oil and other insulating materials. I will be focusing on the measurement of unknown value of capacitance of a capacitor. The most commonly used AC bridge for measurement of capacitance is Schering's bridge, and it also works on the principle of balancing of your load on the arm. So the idea is to make the detector current to be 0, and once the detector current is 0, you can say that the bridge is balanced, and then we will go for solving the network equations. Now here the arm AB constitutes a capacitor C1, which is an unknown value, whose value is to be, or whose capacitance is to be determined. So this is connected or represented as a series combination of C1 with R1. Now C1 is a practical capacitor. So practical capacitor, in the sense, we will always indicate your practical capacitor as a capacitor in parallel with or in series with resistance to indicate the loss in the capacitor. Now C2 is a standard capacitor which is free from losses, and so we are not having a resistive component in arm AB. And now coming to arm BC, it's a non-inductive resistance R3 connected in BC, and in the last term we are connecting a variable capacitor which is varied in order to determine the value of the unknown capacitor, and we also have a variable resistor R4 which is connected in parallel with the C4. Again, the purpose of variable capacitor and resistor is to vary the values or capacitance and resistance values in order to make the bridge balanced and bring the detector current to be 0. Now once the bridge is in balanced condition, what happens? The equations remains the same. E1 equal to E3 here in this case, and E2 equal to E4. Okay. Now once you do that, what you will get is that I1 into R1 plus 1 by j omega C1 equal to I2 into 1 by j omega C2. So this is the equation that you obtain. then this arm. Similarly, once you have the second condition, E2 equal to E4, you will have this I1 into R3 equal to I2 into your capacitor C4 parallel with R4. So R4 by 1 plus j omega C4 R4. That you will get. Okay. So that's the value of these are the two equations that you get. Now again, just like in the inductance bridge, what you can do is you can divide these two equations and then cross multiply. You will be ending up at this particular equation. So you'll have R1. So this is actually R1. So this is R1 plus 1 by j omega C1 into R4 plus 1 by j omega C4 R4 equal to 1 by j omega C2 into R3. So this is the value you get. Now you expand the terms and then you can simplify it and you can group the real and imaginary terms together. So once you compare the imaginary terms, so these are the imaginary terms, so what you will get is that R4 by C1 equal to R3 by C2, R3 by C2. So from that you will get the value of C1 as C1 equal to C2 into R4 by R3. So this is obtained by equating imaginary terms. Now similarly, once you equate the real terms, so this is your real part and this is the real part of the RHS. So once you equate these two, you will have R1 equal to R4 and R4 gets cancelled. R1 equal to R3 C4 by C2. Okay, where R1 is the R1 indicates the lossy component of the capacitor. So this is obtained by equating real part. Okay, so in this way you are able to find out the components of unknown capacitor C1 as well as the value R1 with the help of a balancing condition of the bridge. So thank you so much.